students, welcome to lecture number 31. So, we have been discussing about different length scale in materials or material science actually. There are different aspects of these we have started discussing. In the last lecture we started discussing about CALPHAD as the calculation of the phase diagrams. So, we will discuss more on that, and at the end of this lecture we will talk about a new technique called phase field simulations. But I want to clarify one aspect regarding this part of the lectures. So, you must be thinking that starting from machine learning and then discussing about deep learning, why you are moving into this length scale aspects of materials, because this course is about materials design using machine learning and deep learning, right. So, therefore, material design means design from the atomic sticks to the ball scale. That is what we understand as the material design. If you have studied to undergraduate level, you must have done design of a component as a part of your course curriculum. So, there you start with a certain kind of a small objects, then assemble in there and make a bigger system. So, in terms of the materials, we start with atoms or rather electrons. You will see that in 1 or 2 lectures later, that we start with atoms and then we build crystals. From crystals we will build the material, and finally we build a component which is meter or centimeter level. So, in this sense we need to know how this different length scale will play a role in designing process of a new material or discovery of a new material. That is one aspect or the major aspect of this discussion, but there is another part of it. So, if you want to generate data artificially, or let us say you want to generate data by calculations, not by experimentations, then this computational thermodynamics, phase field simulations or MD simulations or DFT simulations will allow you to do that. That is one of the way of generating data and using that data for further machine learning and deep learning. So, that is why these techniques, it is important that you know these techniques quite well. But we have time constraints, as you understand, we cannot teach you every topics in a detailed manner. I am trying to teach you machine learning, deep learning aspect in a detailed manner, but this requires a much more discussions, which is not possible with given the time frame, but nonetheless you are getting a sense of it and you can build on by reading different books, papers, or maybe attending a course on computational material science. So, these are the two key reasons why we want to study this particular portion, because if you have a knowledge on these length scales of the materials, then you can build lot of different models. That is the thing I wanted to clarify to you. Now, let us get back to the lecture. So, we will talk about material design different length scale part 3 today, and let us talk about what we have learned in the last lecture. So, first and foremost thing is thermodynamics, because thermodynamics gives us the information of the phases and microstructure. So, what are thermodynamics can do? Why do you study that? Because we are interested in the properties of material, or rather we want to design materials with target set of properties. That is what is a requirement, right. So, now what are the properties we are interested? I taught you already mechanical, electrical, magnetic, thermal, chemical and many more, and I have given quite a bit of lecture on these aspects, how to connect structure with properties. These properties are completely dependent on the structure of the material. Structure means atomic structure, crystal structure, microstructures, defects, or even distribution of the phases, right. These two are connected to each other. Now, structure is basically determined by how you make a material, what are the processing routes you are going to use it to make a material. That also we have discussed in the beginning of this course. For the lecture from lecture 3 to lecture 14, we have discussed a lot about that. And in processing we have different parameters to control, like temperature, pressure or stress, volume or strain, chemical composition or the system chemistry of the material system. This all we can change. By changing them we can process a material, and by doing so we can control the structure, which in turn control the material properties. So, that is the main aspects. So, thermodynamics, that is why the basis for understanding any material response to the changes in temperature, pressure, chemical composition, and that is why it is the most critical link between the processing and the microstructure, and we need to know these aspects very well. Let me tell you, these three important pillars, processing, structure and properties, finally determine the performance of the material system. So, at the end of your discovery of material, design of materials, you are going to develop a system, right? You are going to develop a device, and what your interest is the performance of device. Just like your mobile phone, you are interested in buying the mobile phone because this gives you a lot of important advantages, and you are interested in performance of the mobile phone, right? That is why. So, same thing happens in a material system also. So, with this, what do you need to do? So, you understand that is what is thermodynamics is. Now, thermodynamics provides us the information of the phases in the microstructure. That is what we call a CALPHAD, which is nothing but a calculation of phase diagram. So, this can take informations from first principle calculations, which we will discuss after this part of the lecture, also from statistical thermodynamics. I am not sure whether you have idea about statistical thermodynamics. That is a branch of thermodynamics which talks about equations, statistical aspects, and we can also get information for first principle calculations like ab initio calculation like DFT, molecular dynamics calculations. So, these informations starting from calculations of theory can provide important inputs to the CALPHAD, but that is not all. We can also get information from experiments, you can see here, right. So, these three things, experiments, first principle calculation and statistical thermodynamics together can provide information to CALPHAD, and this CALPHAD then can be used to predict phases and microstructure. That is the most important information you can get from the CALPHAD calculations. So, it is an integration of data science with the approach of thermodynamics. That is why we call ICME or integrated computational materials engineering approach. So, this data which we are obtaining from different sources can be either thermodynamical properties like entropy, enthalpy of Gibbs free energy, this one, or you can also have thermal expansion heat capacity data, that is called thermodynamic properties. You can also have kinetic parameters like diffusion coefficients, shear viscosity of liquids, mechanical properties like elastic properties or plastic properties, as well as lattice parameters and interfacial energies or interfacial properties like electronic structures, stacking Fourier energies, twins, dislocations, all these aspects. So, these are all can be obtained from these calculations or even experiment also. So, these all together basically constitute a lot of data, that is what we are talking about. So, now we have to integrate these data science which you are getting from the CALPHAD or with the CALPHAD, then only it can provide you the best possible informations. So, we have to capture data first, experiments carry out computational aspects of data, computational means ab initio or statistical thermodynamics, and then we have to assess the data whether they are good for modeling or not. And after it is assessed, you need to optimize the data for particular material system. So, finally, once it is optimized and we are happy with the assessments, we can store it in a database, and that database then you can buy or use it. That is what normally scientists do. They buy these databases from the standard vendors and then use the databases for calculations of phase diagrams. And once you have done the phase diagram calculations, you can always validate with experiments. That is what it is. So, now, so therefore, in thermodynamic database we will have informations of the assessments, how it has been assessed, and it can also be informations from the literature also. So, it is nothing but an assembly of lot of input data, and which in turn can provide Gibbs free energy models for the different phases. That is another aspects which it can do. As I told you, CALPHAD had 4 or 5 different aspects for data capture, critical assessments, the preprocessing of data, and optimization, storage and validations. The most important one is the, obviously everything is important, most important one is out of this is capture, assessment and optimization. Okay. Then storage and validations can be done much easily. So, as you know that this is the whole cycle of CALPHAD. So, you have to capture data, it can be from liquid, solid, different phases, and then you can do assessment and the optimization of the free energy functions. So, this equation we will talk about now, and finally, we can predict phases, microstructures by using thermocouple calculations. Thermocouple is a particular software which is devised by this some company, but it is basically CALPHAD calculation. One can do diffusion calculations, one can also do calculation based on both transformation as well as thermodynamics, which is called prisma actually. So, let us go back to the board and explain about it. So, CALPHAD as you see is nothing but calculation of phase diagrams. So, what is important information you need is the free energy of the phases. So, if I have to discuss free energy of any phases, it has three components as I told you. It has a component of the pure elements, that is Gi0. Okay, if it is a system of different components, I stands for the components, Gi stands for the free energy of the pure components, that is why I put Gi0, that is for the constitution components, and this is coming from the entropy contribution. The moment you mix different elements, you are going to have a change of entropy, that is calculated from Boltzmann statistics, that is why it is RT sigma xi ln xi. And you have also have another extra component called excess free energy. If this part is not able to explain the free energy of the system, which is always the case, then we can actually add excess component which can take care of that. So, anything which these two components cannot, these two parts cannot explain the free energy of system can be taken care of in excess free energy. And how it is written, excess free energy is written like this. Let us say there are two components m and n. So, this is that, and then this is the interaction parameters between them, and here gamma is exponent, right, that is what it is. So, once you get so calculation of excess free energy is difficult, there are different model exist, okay, which we will not go into details of that. Once you get the free energy total G of the system, then you can sum it over with all these components in the phase, and then that we minimize. This is the main aspects of the CALPHAD, minimize on the free energy. Once you minimize, we can actually do all kinds of calculations very easily. So, that is the primary aspects of the free energy. So, this is exactly shown here. So, G of all phases in the system, all the phases in the system has to be obtained, and then only you can do this. One can look at this paper by Kuttner Ursula in 1997 in Journal of Metals, details will be provided. So, now obviously free energies may not be obtained for all chemistry, all compositions, and that is why extrapolations are important. Not only extrapolation important for that, extrapolation also important for if you want to go from higher order system or 2 component system to 3 component to 4 component system or higher, like binary to ternary to quaternary, you may not have information available. So, what you do is basically you do extrapolation of the free energy functions and then finally obtain global free energy. So, extrapolation can be done by Muganianu or Kohler or Tupps equations. This I am providing you in front of you, you can actually check that, and is else are basically interaction parameters, 0 order or first order interaction parameters you can see here everywhere there, and these parameters are connected with the compositions of the or mole fraction of the phases, right. So, now the question is, once you have the free energy functions, what all you can do? You can do lot of kinds of things. You can actually do non-nuclear free energy constructions, you can actually even calculate how the free energy of solid phases will depends upon the order parameters, many other things you can do, but let us come back to an example of that. So, let us talk about this is a free energy function of a particular system, 3 component system ABC, you can see there. So, here we are plotting GM, GM is nothing but G minus this pure component, as you can see here, this is what it is, that GM, and that is the entropic contributions, which is nothing but RT summation of xi ln xi, as you can see xa ln xa plus xp ln xp plus xc ln xc, and then you have this component L, I think I probably have made a mistake, L into xa xc plus xp xc, that is the excess component, that is how the excess component will look like. Okay. So, this is your entropic contributions, entropy of mixing, this is the excess contributions. Okay. So, one can actually write G m like that. So, now once you have G m, I have written total G is like this, that is what it is. Okay. So, once you have total free energy of this model system, you can do lot of kinds of things. Let us talk about few examples, because that is very important. First example is the binary phase diagram. We will talk about both binary bulk and nano phase diagrams now. Okay. So, let us talk about very simple system, lead antimony. See, this is the lead antimony phase diagram, as you can clearly see, it is taken from Okamoto, journal of phase equilibrium. Here you see this is a simple eutectic systems. There are two terminal solutions, was a lead rich, one is an antimony rich, and there is a eutectic at the lead rich part of the phase diagrams. So, these phase diagrams can be easily obtained. That is what this Giolotka et al. Has done in this paper, Journal of Phase Equilibria 2013, and this phase diagram was obtained by them. So, what all equations they have used, let us talk about it a little bit, because you are giving an example of the system. So, I will be taking data from this paper and show you that. So, let us go back and explain how things can be. So, we will keep this particular equation as it like that and do this. So, in particular to lead antimony system, this calculations can be done in computer very easily. So, as you see here again same thing, G as a function of time, sorry, as a function of temperature. Okay. So, it can be given as this again xi G0 I as a function of temperature, and I can go 1 to 2, because there are two component system here, and then you have entropic part xi ln xi, I again can go to 1 to 2, and finally you have that particular excess free energy part I told you, right, I j more than 1, okay, xi xj, same equation which you have used, okay, into summation Li j, okay, b not b is basically mu. Okay. That is what it is. So, this is the free energy functions which you will normally use for all kinds of system, even for binary lead antimony system also. The pure part, the entropic part, and the excess part, correct. So, I will not go into details of that. As you can see here, that for excess part we can use Redlich-Kistner polynomial, the excess part, excess free energy. One can use Redlich, Kistner polynomial for excess. What is that? Thus, nothing but that is nothing but x a x b, a b are two components here, summation I L okay, into x a minus x b to the power gamma. That is what it is used. Okay. So, this is the excess free energy for the system, and L is written, L is given by another polynomial, I think is written as A plus B T plus C T log T. Okay. That is a function of temperature. So, with this you can model this phase diagram easily, and as you know here there is FCC phase lead, Romerdel antimony. Okay. And in this paper if you look at, it is from Giolotka et al. They have even calculated the activities as a function of mole fraction of antimony. They more or less follow the straight lines, that is Raoult's law, enthalpy of mixing as well as entropy of entropy formations, all of these they have calculated. That is how actually a phase diagram is calculated or obtained. So, now if I take these systems and make small nano size particles, what will happen? This phase diagram will not remain same as what we have shown you. I have shown you here. This will not remain like this, it will change, it will modify. So, in order to modify that, you need to add certain terms, like for these cases when you have a small size particles, your surface area is very large or volume to area is very large. So, therefore, you need to take care of that, and in order to take care of that aspects, what you do is you simply add surface energies or surface tension data, and surface tension also need to be calculated, because surface tension is not constant for all the compositions of the phases. As you can see here, antimony phase solution is stable for some composition range, lead D solution also stable for sub composition range. We marked as alpha as a lead D solution and beta as antimony D solution. Okay, that is what it is done. So, we can write down beta as antimony. So, this solutions are present. So, we need to calculate the surface energies. You can see surface tension as a function of antimony, as a function of antimony for both the solutions has been calculated, and that is what can be used for your modeling. So, let me just tell you what is the main aspects of this. Main aspect of this is what you have to add a surface energy term, and that surface energy term is what is important here. Why it is important? Because your nanoparticles are small. So, for that what we do, we add a extra energy term. So, that energy term will be added to the G. So, G total for nano system, for nano, G total will be G, this G, GT plus G of interface, correct, because you have lot of interfaces due to small size, surface area is very large, and this normally are calculated using. So, therefore, this is G T plus summation I think is gamma I, the surface energy, or let us not use gamma you have already used, sigma I, this is surface energy. Okay. This is also a function of composition and temperature both, okay, into A I, this is function of temperature, composition as well as number of moles present, correct, that is what it is. So, we are adding an extra term, this term which is nothing coming from surface area. So, surface energy, relative surface energy into surface area, they are multiplied, added together for all the particles. So, one can use different kinds of surface energy models. So, for this kind of particles which I have shown you, okay, this kind of particle, they are two phase particles, you can see here some of these microstructures here, clearly you can see here in this here, okay, or here you can see that there are two phase particles, here also you can see, right. So, therefore, the surface area calculation or surface energy calculation will be not easy. So, what is done here is that this will be equal to G T, the free energy, plus surface area of alpha phase, surface energy of alpha phase, plus surface area of beta phase, surface energy of beta phase, plus interfacial area of alpha and beta, and surface energy of alpha and beta. Okay. So, you have a particle like this when you have two phases alpha and beta. So, this is the surface area of alpha, this is the surface area of beta, and this is the surface area of this one is alpha beta. Okay. And we are multiplying everything with surface energy, you can see that. So, that is what your G G total. So, now the modeling becomes little bit complex, but one can do that. One can do that. You can check this paper which is coming from my research group, and you can find out this modeling in detailed manner. So, you can see that phase boundaries will change as a function of size. If I take 45 and 35 nanometer particles, you can see the phase boundaries are changing. So, slowly this eutectic temperature is going down, eutectic composition is also shifting. You can see that this point which is here is shifting to this point, and temperature is also going down. That is something which is very important features in our systems. So, we can not only generate the data for the bulk system, but we can also generate data for the nano systems also. If you are talking about any nanoparticles or something, you can actually do this kind of calculation very easily now using your console and generate a lot of data, and you can use this data for your further modeling. So, this one I showed you in the last lecture. We can even go for multi-component systems like 5 component systems here, different kinds of systems forming FCC and BCC solutions, and there we plot, after calculation we plot the phase diagrams like this, mole fraction of the phases versus temperature, and here you have only 3 phases, liquid and 2 solid phases. Here you have more than 4 phases. So, depending on the number of phases, you can plot it for each of the phases and look at the relative stability. That is what can be done. So, one can actually do even for calculations for whole phase diagrams, like for this system FCC1 which I showed you, or this one manganese, iron, cobalt and nickel, we can vary composition from 0.05 to 0.35, the 5 to 35 mole fractions, and we can plot at 1000 Kelvin, this is at 1000 Kelvin, we can plot this kind of diagrams, we can show the relative stability of this phase very easily. Well, I would also like to tell you that although CALPHAD is a very powerful tool, but CALPHAD is not only the tool which can be used for calculation of phase diagram, one can do from first principle calculation also, like this one. This diagram is calculated obtained from PANDAT, I acknowledge their calculations done by PANDAT, and you can see here we can actually do this metastable phases, phase boundaries for the metastable phase here theta prime, which I talked about it for aluminum copper alloys earlier also, and you can see that how the metastable phase boundaries can change. So, that we can do from the first principle ab initio calculation also, but these are time consuming, takes a lot of computational power. Nonetheless, these calculations are refined, so it can provide you more informations. So, that is it, and also one can do edging response also. One can actually calculate how the edging can change the mechanical properties like yield strength. As you can see here, different temperature, different time, we can obtain the edging curves also by these calculations. This is possible to do that. Well, so in a nutshell, we have to use advanced computational material science tools. You can reduce the need for costly and time consuming experiments. We can do alloy designs like crystal structure data. We can calculate the phase diagrams. We can also do microstructure, which we will talk a little later, part of the lecture today, and one can also predict mechanical properties. So, what you need is basically these integrations of first principle calculations, CALPHAD, phase field simulation, as well as micromechanical models. So, these are the things you need to know if you want to integrate machine learning with these models. So, let me stop here for the first part of this lecture. We will get back to the next part of the lecture, and we will talk about phase field simulations more details.